All right, in this explainer, we're going to go inside the very bones of our modern world. We're going to look at the invisible science that's holding up our cities, that incredible hidden strength of reinforced concrete.
So let's just jump right in with a question. It might sound a little absurd, but it's really at the heart of all modern engineering. Think about it. You're standing inside some huge concrete building right now. Why doesn't it all just snap in half?
Okay, to answer that, we've got to understand the material itself. Concrete, it's this miracle of construction for sure. But kinda like a superhero, it has a critical weakness, a fatal flaw, really. And it's one that engineers absolutely had to solve.
And here's the thing. Concrete is not new. Not by a long shot. I mean, we've been using some form of it for like over 10,000 years. Just look at the Roman Pantheon. Get this, its incredible dome was built almost 2,000 years ago, and it's made of unreinforced concrete. And it's still standing. So you gotta ask, right? If it was so great, what was the problem? What needed fixing?
Well, it turns out this ancient material has a total split personality. It is unbelievably strong when you compress it, when you push on it, squeeze it together. But the second you try to stretch it or pull it apart, a force that we call tension, it just becomes super brittle and cracks. And that's its fatal flaw.
So the big question is, how do you build these massive structures with a material that just falls apart when you pull on it? The answer, honestly, is surprisingly simple. You give it a partner that can handle being pulled. And this one partnership, well, it would literally change everything.
Okay, this right here shows the solution perfectly. So just imagine a simple concrete beam, right? You put a load on it and the top part gets squeezed together, it gets compressed. Concrete loves that stuff. But look at the bottom part. It's getting stretched out. That's tension. And boom, it cracks. So what's the fix? You embed a steel bar, what we call rebar, right inside the concrete. Exactly where that tension is going to be. Because see, steel is fantastic in tension. So now you've got the concrete handling the compression, the steel handling the tension, and the whole beam holds up. It's just a perfect team.
All right, so now we've got our super material. Let's move on and see what it's actually up against. Because every single second of every single day, our buildings are in a constant fight against this barrage of forces. And engineers have a simple name for them: loads.
And these loads, they basically come in three main flavors. First up, you've got your dead loads. That's just the building's own weight, all the permanent stuff, like the beams, the columns, the floors. Then you've got live loads. That's all the temporary and movable stuff. You, me, our furniture, maybe some cars in a parking garage. And finally, there are the environmental loads. The really unpredictable forces from nature. Wind, earthquakes, a heavy pile of snow.
But here's the kicker, right? The real world, it's messy. Loads are never perfectly predictable. Construction is never 100% flawless. So how in the world do engineers design for a world that just refuses to follow the blueprints exactly?
Well, it all boils down to one simple, fundamental rule of safety. The structure's strength, what we call its capacity, has to be bigger than the forces being put on it, or the demand. Capacity must be greater than demand. Sounds simple, right? Yeah, but actually making sure that happens? That is way, way harder than it sounds.
And that's because there are just so many sources of uncertainty. I mean, think about it. The actual loads could be heavier than you assumed. The concrete you got on site might not be exactly as strong as the sample you tested in the lab. A beam might be off by a few millimeters. Maybe the steel rebar isn't in the absolute perfect spot. And on top of all that, every analysis, every calculation has to simplify things a little.
So to deal with all this, engineers use this really clever two-part safety system. Part one is basically to be a professional pessimist when it comes to the forces. They use something called a load factor. You'll see it as the Greek letter gamma. And it's just a multiplier that's bigger than 1. They take the loads they think will be there and they multiply them. So they're designing for a force that's way bigger than what they expect, just in case. They're deliberately overestimating the demand.
Okay, so for the second part of the solution, they are just as pessimistic, but this time about their own materials. They use what's called a strength reduction factor. That's the Greek letter phi. And this one is a multiplier that's less than 1. They apply it to the calculated strength of their materials. It's kind of like saying, okay, I know this beam should be this strong on paper, but I'm just going to assume it's a little bit weaker, just to be on the safe side. They're basically underestimating their own capacity on purpose.
So you take this double-layered pessimism, right? You overestimate the bad stuff, the loads, and you underestimate the good stuff, the strength. And the result? It's pretty astonishing, actually. By combining these two safety factors, engineers can design buildings to a target probability of failure that is just unbelievably small. We're talking about 1 in 100,000.
This entire approach to safety in building design, it's actually a pretty modern philosophy. It grew out of an older, maybe more straightforward way of thinking. And looking at the difference between the two really shows you just how much engineering has evolved.
So the old method was called working stress design, and it was all about keeping the materials happy, in their comfort zone. A good way to think about it is making sure the building never even breaks a sweat. But the modern method, ultimate strength design, totally different ballgame. It intentionally imagines a worst-case scenario, a hypothetical overload, and then designs a structure to be able to survive that crazy event, pushing the materials right to their absolute limits.
And this quote right here, it really gets to the very heart of the modern engineering mindset. It says that design is based on the best available estimate of the actual strength. Now that phrase, best available estimate, that is everything. It's engineers admitting that their calculations are just that, an estimate. And that entire system of safety factors we just talked about, that's what exists to bridge the gap between their perfect calculations on paper and our very imperfect world.
And that really just leaves us with a final thought, doesn't it? This really elegant philosophy of planning for imperfection, it's not just in our buildings. It's a way of thinking that props up so much of our modern world, often in ways we don't even see. So the next time you walk into a big building, just remember, it's not just concrete and steel holding you up. It's a powerful and honestly a deeply intelligent idea about safety.